Hello everyone! So, in this video, we will explain about our final project which is Calculus 3. Let's get started! Before we get into the explanation, let me introduce our team which is Aurora, Maria Degli, and also Silvi.
So this is a table of content. There is introduction, literature review, research method, result and discussion, and the last is conclusion.
First, I will explain the background in Chapter 1. In the competitive landscape of industrialization, companies facing diverse product demands must effectively manage spare part inventory to maintain their competitiveness. The goal is to meet customer demand while minimizing unfulfilled requests, measured by the fill rate. Researchers like R.G.A. Baston and Gigi van Houten have developed models focusing on efficient inventory control, resulting in a significant cost reduction. Similarly, engine Topanzi, Pelin Bayindir, and Tarkantan have discussed methods for optimizing spare part inventory system, emphasizing minimal inventory level and efficient order strategies. These studies underscore the importance of strategic inventory management in saving operational excellence amidst intense competition. The next is problem statement. The problem statement for the final project is how to develop a spare part inventory model considering different customer classes. What is the influence of different customer classes in minimizing the total cost of spare part inventory? Okay, the next is problem limitation. The scope of the problem to be discussed is the differentiation of a customer classes grouped based on the number of requests per year. The spare part used is the final project are the 10 main spare part of a server machine from PTXYZ. The data is full of Poisson distribution. Okay, the next I will explain about the objective in chapter 1. The objective of this final project are as follows. The first is to develop a spare part inventory model considering different customer classes. The next is to minimize the total cost of spare part inventory. The next is benefits. The benefit of this writing are to obtain a spare part inventory model with different customer classes to minimize the total cost of spare part inventory by applying the Lagrange multiplier method. The next is writing systematic. The first is chapter 1 introduction. This chapter explains the background, problem statement, problem limitation, objective, benefit, and writing systematic. The next is chapter 2 literature review. The chapter explains the understanding of spare part inventory, definition, inventory control system, probabilistic inventory control model, Poisson distribution, lead time, fill rate, and metric theory. The next is chapter 3 methodology. This chapter outlines the problem solving process and project objective. The next is chapter 4 discussion. This chapter delves into model determination, queuing theory application, fill rate, minimization via Lagrange relation, and decomposition, and Poisson diamond testing through numerical simulation. The last is conclusion. This chapter explains the conclusion obtained from the discussion and recommendation. Okay, the next I will explain about chapter 2. The first is spare part definition. Machine spare part encompasses the first component serving specific function. Categorizes into three types based on repairability. The first is non-repairable, the second is partially repairable, and the last is fully repairable. The next is inventory definition. Inventory encompasses material or goods stores for production. Resale are spare parts serving to meet demand, mitigate uncertainty, and speculate on prices. Types include raw materials, work in progress, finished good, supplies, project materials, and merchandise. Inventory control involves planning, implementation, and supervision to optimize availability while considering extreme cases like big order and lost sales. The next is inventory control system. Inventory costs comprise six types: purchasing, ordering, holding, stock out, risk of damage and loss, and safety stock. Purchasing costs are per unit prices, ordering include administrative and shipping expenses, holding depends on average quantity stored, stock out arise from delays or insufficient stock, risk encompasses damage and loss, while safety stock prevents stock out, incurring addition costs. Okay, the next in chapter 2, we have the lead time. Lead time is crucial in inventory management, especially for spare parts. It's the time for ordering to receive, directly impacting stock level. It's vital to setting reorder points, ensuring timely purchases to avoid overstock or stockouts. Lead time varies per part is tailored to company condition. The next we have Poisson distribution. A Poisson experiment generates value for a random variable x, representing outcome in a time interval or region. Key characteristics include no time interval per region dependence, probability proportional to time per region size, and negligible probability of multiple outcome in small interval per region. The Poisson random variable x has a probability distribution p x mu, where mu is the mean value. The next we have metric theory. Metric theory integrates queuing theory to optimize spare part distribution. Focusing on distributor improvement, it assumes demand and lead time independence. With demand following a Poisson distribution, stock control utilizes a big stock policy, and the spare part inventory model calculates fill rates for each customer class. Farm theorem is used for steady state probability distribution, and backorder are determined using pipeline stock size based on average demand and lead time. So this is the illustration of spare part inventory model in metric theory. Okay, this is the last page in chapter 2. We have the Lagrange multiplier method. The Lagrange multiplier method solves constraint optimization problems by transforming them into unconstrained ones. Contour condition ensure optimality. To optimize total inventory investment, a nonlinear integer problem Lagrange multiplier are effective. By decomposing the Lagrangian relation function, solving becomes easier. Checking convexity of the objective and constraint function ensure obtaining the most minimal solution. Convexity is confirmed through condition on first and second derivative. A solution is considered the absolute minimum. It is lower than all the feasible points. And the next we have fill rate. Fill rate makes sure the percentage of requested items available to customers when needed. It's calculated as the number of fulfilled items divided by demand, expressed as a percentage. It can be assessed by per product or overall. Tailoring fill rate target for each customer and item optimized supply chain management, reflecting strategic priorities. And the next is queuing theory. Queuing theory deals with customer arriving at a service facility. Forming a queue model consider arrival and service time distribution. Candles notation summarize queue characteristic. For multiple parallel service channels, notation like ABC divided by DEF is used. Balance equation determines steady state probabilities. For example, in M per M per 1 per infinity, a single channel single server system equation use average arrival and service rates. Similar equation apply to multiple channel system, assuming position, arrival, and expositional service time distribution. And this is the illustration of queuing system.
Okay, I will explain about the research method. First is development of a mathematical model with creation of objective function and restriction, metric theory and fill rate, also Lagrange multipliers, decomposition, and critical level of spare parts. And the second is base of simulation with the utilization of MATLAB software. And third is final research stage of writing the report, like a conclusion and recommendation. And the last is identification of problem and search of supportive theories on inventory management, Poisson distribution, Q theory, metric theory, and the last is Lagrange multipliers method. So I will explain about the result and discussion. First is spare part definition. So our warehouse model accommodates 10 primary SKUs with customer demand following the Poisson distribution. So notably, customer classes influence the fill rate, where class 1 customer experience a higher fill rate compared to class 2. And this is difference is mathematically represented as a follow, as you can see in the 4.1. And spare parts replenishment involves independent and identical items for customer class G more than one, and the fill rate is more than equal customer class K less than G. So ensuring minimum inventory G more than equal minimum inventory K as follow, as you can see in the picture 4.2. And next I will explain about the critical level analysis. So in the critical level analysis, there is the fill rate formula, which stands for queuing theory principle. So plays a pivotal role in establishing the critical value level value essential for efficient inventory management. So it enabled us to gauge the optimal balance between inventory levels and customer demand. So for each spare part I in customer class G, the fill rate for each spare part is, as you can see in the 4.3, where Mi is the main demand for item I. So I will explain the Lagrange realization. So yeah, in this section we employ Lagrange realization to derive solution for function P, and the constant function is applicable to every customer class within the range of G equal 1. So to G this, assuming the from, as you can see the picture 4.4, and then we can move to the sampling optimization with the Lagrange multiplier method. So yeah, in this section we'll derive a solution for the function L lambda, where lambda represents any non-negative factor. So the objective function, which is the L lambda, can be written as a follow, as you can see in the picture 4.5.
So we will obtain a solution to the function L lambda, where lambda is any non-negative factor, which is in the equation. To get the critical level of each spare parts in each customer class, it is obtained by performing the partial derivative of I, C, J, which is J is equal to 1, 2, and etc. Okay, so here is the case where the demand data for 10 types of spare parts from 5 customer classes for 1 year are contained in the Appendix B. The criteria for grouping customer classes are shown here, which is the higher class, so the lessest the demand. So this is the Kolmogorov-Smirnov test using EasyFit 5.5 software for the demand distribution. Okay, now we start to calculate the minimum inventory of spare parts using this equation. So the first step is to determine the spare parts attribute, which is shown in the table. Next, we calculate the fill rate for each 5 classes. This is the way to calculate the fill rate for the first class, and then the rest is the result for the other classes. After that, using this equation, we can calculate the I1, and also there is the calculation. And then, using this derivative formula for each classes, lastly, we will get into long calculation to get the D.
So finally, we're in the last slide, which is the conclusion. So the conclusion is the goal of spare parts inventory management is to meet customer demands and maintain service levels while minimizing unmet demands. Researchers have developed multi-echelon models to manage spare parts inventory, emphasizing lateral and emergency deliveries, achieving an average cost reduction of over 3% compared to previous methods. So the demands for spare parts follows a Poisson distribution with different ranks for each customer class. A new model introduces queuing theory and uses the Lagrange multiplier method to optimize parts availability, focusing on minimizing back orders. So this approach addresses customer class difference in the fill rate across 10 main SKUs in a warehouse.
Thank you for watching. Bye bye.